Welcome to the lesson video on polynomial regression and step functions. In this video, we're going to talk about polynomial regression and step functions. So what are these? So polynomial regression is a regression, meaning we're predicting continuous valued outputs based on some input variables, in which the functional form for the f hat, the relationship between inputs and outputs, might be a polynomial function. So generally it'll look something like this little cartoon. We have a bunch of an input x, output y, data points shown in green, and we're going to find some polynomial that fit those. Step functions, and we're going to use piecewise linear functions as well, is where the f hat has a form of a step function and eventually piecewise linear functions. And so there's a step function, the plot. Let's get a marker here. This plot shows our relationship being a step function. The red line shows us the graph of f hat. We're estimating that step function based on the inputs. On this, we have a piecewise linear function. A step function is a function that's constant on a couple of intervals in the input variable. Piecewise linear function is linear, and it's had different linear function on each of the inputs. And generally, as we show here, the places where our two linear functions meet, it's a continuous value there. So where they meet, they have the same value at the crossover point. Why would we do this? Well, some outputs just have relationship with their inputs that are better modeled by polynomials or piecewise linear step functions. And so this gives us more flexibility in using f hat to match a relationship between x and y. Improved accuracy, better understanding, and improved prediction performance. So a little more formally, polynomial regression, we have our y's. So yi is the ith sample in y, and then we have our x. And so here xi, we're only doing one input variable, so this is single variable polynomial regression. And so we have some polynomial function of those xi's. And so we're going to have yi be this function shown here, the xi's. It's a polynomial plus our error. And then we're going to compute the mean squared error of those estimates of those yi's based on those xi's, and then find the coefficients that minimize that mean squared error. So in a lot of ways, the same thing we do with linear regression, we're just going to use polynomial functions. Here's an example. On the left-hand side, we're taking a fourth degree polynomial, doing least squares regression of wage as a function of age. And this is an example where you can imagine why there's some sort of nonlinear relationship. At low ages, people are starting their careers, and so they're not making as much. As they progress, they move up in the hierarchy within their career, and at some point they reach some of the higher ages, 40s, 50s, and 60s, and then after 60, we tend to get people in the retirement ages, and they're taking lower paid jobs perhaps, and so we get a decrease. And in fact, in this polynomial, you can see that the increase through the early years, it seems to be steeper than the leveling off through the later years. On the right-hand side, we have fourth degree polynomial to do logistic regression, and it's regression to predict the probability that wage is greater than 250,000 as a function of age. And so we have this peak here of able about 40, and then this later peak. I don't know, it's sort of interesting that the middle 45 to 55 range is a little bit of a decrease in that probability that wage is going to be exceeding 250,000. But we see some interesting structure and things that we wouldn't learn if we tried to do these with strict single linear regression or standard logistic regression. We can do similar things with step functions. On the left-hand side, again, we're predicting wage as a function of age. We don't seem to have as good of a fit, but something is interesting. We have these three different stages in a career, maybe teens through early 30s, and then mid-30s through, say, 65, and then 65 and above. And something similar, these are giving us a rougher shape. Generally, step functions aren't used for prediction a lot. They're used as a building block for more complicated functions. So the piecewise linear function that we talked about earlier is really what we might care about. We might do piecewise linear function, which might give us something like that for this region. And so the step functions allow us to subdivide the domain up into parts, and we're going to look at having different functions on the different parts in later videos. So choosing a regression model, how do we choose these? we have to compare our fit in error and prediction performance using cross-validation of these more complicated models to choose, say, the degree of the polynomial or whatever functional form we're going to choose for our regression. We also use scatter plots as a guide. We want to look for nonlinear relationships. For example, if I just look at the scatter plot that we've been talking about a couple of times, wage as a function of age, I might look at this and say, hey, there's something that's nonlinear going on, and maybe I would guess a second degree polynomial, and I would try a fourth as well just to try it. And it seems like the fourth would be a good predictor based on our plots from previous. We also have to be aware or need to think about this as a standard bias variance trade-off. So as you increase model flexibility and you choose a more flexible model, that has greater variance error, so greater potential for error for variance error. And so the only times we want to do that is when the trade-off gives us a benefit from that by removing bias error, meaning that bias error is having a bias that's in our model that doesn't fit the data. Right? The model assumes the relationship is linear, but the relationship is not linear. That's going to introduce bias error. We can get rid of that bias error by picking a relationship for our model that better fits the relationship that's in the data. So review, we've talked about polynomial regression and step functions. Polynomial regression, we allow a polynomial for the functional form for f hat. Step functions, we allow piecewise linear functions or step functions as a functional form for f hat. Really, I mentioned piecewise linear because we don't care about step functions themselves. Step functions are really a building block for more complicated functions. Thank you very much for watching.